In this video we're going to go through a couple of the problems that were on the dynamics problem set and also a few other common Newton's laws types problems that we could expect on the AP exam or our test coming up. This first one is the box problem that we spoke briefly in class. That was on our dynamics problem set. Two boxes have masses M1 and M2, where M2 is the greater mass. It's visually larger in the picture. They're being pushed across a frictionless horizontal surface. We're saying they're pushed to the right. You can see that pushing force vector is represented by the blue arrow in the diagram. In which arrangement, the first one, A, to the left, or B, to the right, does the force that the left box applies to the right box have a greater magnitude? Or C, is the magnitude the same in both cases? So we're going to do this one by applying our Newton's second law, which in mathematical form says sigma F, or the net force, or the sum of all the forces on an object, is equal to the mass of that object, or the total mass of a system of objects. In this case we have two objects, so we can think of it as an entire system, times the resulting acceleration. That net force is always in the same direction as the final net acceleration, and it is of proportionate magnitude. So I have that boxed in pink, and when I think of the total acceleration of this system of objects, mass 1 and 2, I need to add their masses together. Pretend like it's one giant object. Those two masses, imagine box 1 is put in box 2, and now all of that mass is just one box, which is the sum of both of them. I would have to consider all that mass to determine its resulting acceleration from this pushing force. I can then talk about each individual object as I've done on the left and the right there. I can talk about the sum of the forces acting on box 1 equals the mass of 1 times the acceleration, and the sum of the forces acting on box 2 equals the mass of box 2 times the acceleration. Each of those objects can be investigated individually, and I'll draw free body diagrams for each individual box in each case, case A and case B. That first red force is the force of push on object 1, and then I have the force 2 pushing back on box 1. That's the box 2 pushing back on box 1 in the left diagram. My Fg for box 1, which is the force of gravitation of the weight, is equal to m1 times g, and the normal force, we know there's no acceleration in the vertical direction or the purple direction here, so those normal forces balance out with the weights of each respective box. I've labeled the box like the diagrams 1 and 2, so you can see that box 1, for just scenario A, box 1 has both the pushing force acting to the right and also the blue force, the force of box 2 pushing back on it. And then you see in my free body diagram number 2, still for scenario A, is for the larger and more massive box M2, and it just has the force of 1 pushing on it, or F1 on 2. The resulting forces on each of these are going to be the forces that actually accelerate them, and they have the same acceleration. If they didn't, then they would separate in terms of the space or distance between them would change, and they wouldn't both be pushed at the same time anymore. Before we go on to the free body diagrams for the other one, regarding the bottom left corner, I've written out from each respective free body diagram the sum, starting at the bottom left over here. The sum of the forces acting on box 1 is m1 times A. That's the force of the push minus the force of box 2 pushing back on box 1 equals m1 times A. That force of 2 is also diagrammed over there to the right, just right here. I've looked at my free body diagram number 2, and I have the sum of the forces acting on that box 2 is just the force of 1 acting on 2. The push of that little box on the larger box, box 2. That equals the mass of box 2 times its acceleration. Well, I've just substituted this value, m2a2, in over here for the force of 2 acting on 1. And that's where you see that in the following line. Here's the following line right here. The force of the push minus mass 2 times acceleration 2 equals mass 1 times acceleration 1. In solving for the force of the push, I show down in the very bottom line that the force of that push is simply the sum of the masses times the acceleration, which gets us back to our system of objects can be treated as a single object. Just add those masses up. And we'll come back to this in a moment. Continue on. Now looking at the scenario on the right, scenario B, I'm drawing my free body diagrams. They're pretty much the same except reversing the positions of the boxes. So I have my force of my push now on box 2, and the pushback is of box 1 acting on box 2, and the only force acting on box 1 in scenario B is force of the box 2 pushing on it. Now this time I've given some numbers. I've said in the middle here, let's pretend the force of the push is positive 9 newtons. The mass of box 1 is 1 kilogram. The mass of box 2 is 2 kilograms. F equals ma. 9 newtons equals the sum of their masses, like we said it had to be, 3 kilograms times a. Solving for a, 9 newtons divided by 3 kilograms is 3 meters per second squared for the acceleration of both the boxes. It means each one is accelerating with an acceleration of 3 meters per second squared. I can go back, as I'm doing here on both sides right there and right there, substituting in known values now for the acceleration and for that force of the push of 9 newtons, and be able to solve and see what we can figure out. Here on the leftmost column where I'm writing now, 9 newtons minus m2a2 gives me a final resulting value for the force of box 1 on box 2 of 3 newtons. That's the force of the leftmost box on the rightermost box in the scenario B. We go back over to the left side now. I'm back over here again. I can look at what the value of that force of box 1 on box 2 should be. Substituting in those same values that I had for the acceleration, I find that the force of box 1 on box 2 in scenario A must be 6 newtons. So, going back to the original question, in which arrangement, A or B, does the force at the left box applies to the right box have a greater magnitude, or are they equal? I have to say in scenario A, the force at the first box, there it is down here in this final equation, the force of the first box on the second box in scenario A is equal to double the amount it will be in scenario B. This next one is a problem that's on the flip side of that sheet on Dynamics problem set number 1. I think the first one was problem 15, rank the tension in the rope as it passes over the pulleys in ascending order, smallest first. So in A, it's just the full weight of the block. A is in the tension of the ropes. In scenario B, I have 3 forces of tension that I'd model because of those pulleys. And in look, see, I have 2 tensions. And there's a section in 4, I forget if it's 4.7, in chapter 4, there are a few example problems that specifically use these pulleys. We won't see too much beyond the conceptual stuff that involves pulleys. But we'll get back to it a little bit when we talk about work. This last one down here, 10 kilogram block is connected to a 40 kilogram block as shown in the figure. The surface that the block slides on is frictionless. A force of 50 Newton pulls on the block to the right. What's the acceleration? What's the magnitude of the tension? I'm going to do free body diagrams for both of these. The diagrams just below those masses are connected or represent each of those masses. So 10 kilogram free body diagrams on the left. It just has tension pulling it to the right. The 40 kilogram block has the applied force of 50 newtons minus that tension pulling it in the other direction. Those tensions are equal, but in opposite directions. I have F equals ma for my system, which is 50 newtons equals the sum of the masses times the acceleration. So 50 newtons divided by 50 kilograms gives me my acceleration for the system. So the entire system, like the 10 kilogram block and the 40 kilogram block together, have an acceleration of 1 meter per second squared. So each one individually must have an acceleration of 1 meter per second squared. So I can go back and write out, as I've done in circle 1 and circle 2 up here, just write out the equations that I get from each individual free body diagram and can compare the values I get for t. They both come out to be 10 newtons. So that must be the value for the amount of force and the tension in the rope. Both cases I've simply applied Newton's second law. I've been careful to call to the right positive and to the left negative. It doesn't matter which direction I call positive and negative as long as the resulting acceleration for all the objects in the system are in the same direction. If I have 2 blocks that are moving with one another, then their acceleration should have the same sign and the same magnitude. This next problem is an example of an Atwood machine. An Atwood machine is exactly what's pictured here. It's just 2 masses hung over a single pulley, And in theory, we call the pulley massless and frictionless, as well as the string being massless and perfectly unstretchable. And in this example, we're looking at an Atwood machine in which there's a mass of 2 kilograms and a mass of 5 kilograms. Now, it's kind of like a balance. If you want it to balance, you need to have the same equal masses on either side. So in this case, the acceleration of the system, if we were to place these masses on there and let them go and hang freely, the 5 kilogram object would move down and the 2 kilogram object would move up. But they aren't going to have the acceleration equal to g. The 5 kilogram object will only fall with the acceleration g if there's no 2 kilogram object pulling back in the opposite direction. So we have a few questions here we'll look at. We'll draw some free body diagrams in my gray box, then write the equation for the net force in the y direction equals m times the acceleration in the y direction for both masses, and answer the rest of the questions down there. Let's get going. I have a smaller mass for object 2, so I've drawn a proportionately smaller Fg vector, its weight, which is equal to m2g. There's a tension and another tension. They're both equal in magnitude. And of course I have the weight for my object 1. I've indicated where I believe the acceleration should be directed. I said counterclockwise because, one, I know it, but sometimes we don't know exactly where the acceleration is going to go. We have a problem with pulleys that are set up more complicated than this on an incline that might have friction or not. So you can pick a direction and just say, okay, I'll call the positive direction counterclockwise. That's the way I think they should move. Let's figure it out. Let's see if I can, if it has any acceleration. And if it doesn't go in the positive direction that I've picked, then I'll end up with a negative acceleration if I've done it properly, and it'll tell me, oh, actually it's going to move the other way. But right now for this one, I know it's going to move counterclockwise because the force is greater on the 5 kilogram mass, so it's going to move down. My equation for the 2 kilogram mass is a tension upward. I'm calling that in the direction of the acceleration is positive. So I have t in the positive direction minus the mass of the second object, m2 is the 2 kilogram object, times g, that's its weight, and the force downward, equals the mass of that object, m2, times its acceleration. I then also have an equation to write for the 5 kilogram object, which is m1g minus t. It's accelerating in the positive direction, which I called it's going to be downward for it, and I put my blue arrows near the diagram to indicate that. So if the weight is the force that is accelerating the system, the weight of the 5 kilogram object, m1g, minus the tension pulling back upwards, which is less than that object's weight, equals m1 times a. Why do we not have subscripts for the tension variables? Because it's the same string and they have the same tension. Why do we not need to write the equations for net F sub x equals ma sub x for these two bodies? We have no forces in the x direction. What's the acceleration of the system? I have a little asterisk star, follow it up there because I'm going to write out those two equations for each one again. And what I'm going to do to find the acceleration for the entire system is add them together so I can get rid of one of my variables. So I've, in this step here, pause for a moment. I have written both my equations again. I've shown my curvy arrows there to show which equation is for which object. I've gotten those because I've drawn my free body diagrams and I can see how those equations correspond to those diagrams. And I've highlighted those variables t in green that I have a positive t plus a negative t. T is going to go away. I have positive m1g and a minus m2g, so that's on the left side of my equation after I've added the equations together, and that equals m2a plus m1a, so I have on the right side of my equation. I'm about to factor out g on the left side and a on the right side, because both these objects are connected by a perfectly unstretchable string that has no mass, and they're going to have the same acceleration because of that. So I factor out g and I factor out a. I'm solving for the acceleration of the system, which simply means the acceleration of both those blocks together. And there it is. I can check my units. I have g in meters per second squared times kilograms over kilograms equals acceleration in meters per second squared. And so I can see from my boxed equation there, my pink box with the blue equation inside it, that the resulting acceleration of these blocks is going to be g times some fraction. So it's going to be some fraction of the gravitational acceleration. The most acceleration it's going to have is g. And because there's a string over a pulley with a weight holding back that 5 kilograms from accelerating at full g, it's going to be an acceleration of somewhat smaller than that, some fraction of it. And what values are involved in determining that fraction? The ratio of the difference and the sums of their masses. It's just the masses of those blocks that determine what fraction of g the system's acceleration is going to be. So in this case, I've solved it, and it's 3/7 g. You can see right there, because we've had the literal equation and we've solved it and moved the variables around and factored stuff out, that we can then see how situations would change if we changed the mass. Let's say I had equal masses there. Let's say I had, both of them are 5 kilograms. Then up in my box equation with g, I would have g times m1 minus m2. So if they're both the same mass, that's going to be 0. 0 over the sum of their masses, 10. Which wouldn't matter because it's 0 times g, the acceleration would be 0. So if I want them to balance on my Atwood machine, two masses on separate sides of a pulley connected by a string, the same mass will have 0 acceleration. That's a good way to use that equation to see how would the situation change. I can just change the masses and I can see what would be different. With these particular mass values, 2 kilograms and 5 kilograms, I should have 5 minus 2, 3 over 5 plus 2, 7. The difference of the masses over the sum would be 3/7 g, so it's some value in between 0 and full gravitational acceleration. Last part, looking for the tension in the cord. At this point, I can pick any equation I want that I've already come up with and substitute in my value for the acceleration, which is 3/7 g, or 3g over 7, and find the value of the tension. In this case, I'm doing it with both equations real quick. And I've just substituted my value I found for the acceleration of the system, and I find that the tension in the cord should be about 3g, 20 over 7g. So the tension in the cord is some slightly higher value of what that value just of gravitational acceleration is, times those kilograms. Notice I do have my units. I didn't put units in there for this one. Let's just be clear right here. Check out this line. I've got mass 1, which is in kilograms, times some value of meters per second squared. So this is m1g. I've substituted in the value of m1, which is 5. So in this one I got 5 kilograms times 4/7 g is 27 g kilogram times meters per second squared. So that's newtons. Okay. And then in the top one I have the same sort of thing, m2 times 10/7 g. Or m2 is 2 kilograms times 10/7 g meters per second squared. So I've just kept g as g, so again we can kind of look in there and see how the how that ratio affects the total tension force. If I increase the masses, you can see that that would proportionately increase the value of the force in the tension cord. Alright, so that's a basic Atwood machine. Anytime you take this sort of thing and flip it, put one block on a table or an incline, then you just have to, it's the same sort of deal, you just have to be careful of your directions and watch the any angles that come into play. So here's this is a common one that's just one block. Now, instead of the Atwood machine where they're both hanging, I have the same blocks, but the 5 kilogram block's on the table, and the 2 kilogram block is just hanging. In this one, I'm saying it's a frictionless, massless pulley with a massless string. I think I have do I have any friction on this one? I forget. I have a free body diagram I'm about to draw on the right. Aha, okay, I do have friction. I said the mu-s, the coefficient of static friction is 0.4 between object 1 and the table. Do they accelerate? Now is the question. So we saw before, if I just have the free body diagram of the Atwood machine with the 5 kilogram and 2 kilogram hanging over a pulley, and that's it, there's no table, it accelerates in the direction of the heavier mass, or the more massive mass, I should say. Now we have a 2 kilogram mass hanging over the table and a 5 kilogram mass on the table, and there's friction on the table, and imagine, say, someone's been holding that 2 kilogram mass, and now they let go of it. Is friction strong enough to keep the 5 kilogram mass and the 2 kilogram mass together, since they're attached, from moving? Or is the frictional coefficient too low, and do they start to accelerate? I don't know. Let's find out. One thing we're going to do, just like we did before, draw free body diagrams for objects 1 and 2. we're going to do our F equals ma. I should always say sigma F. That's total forces, F equals ma. For both objects, we'll examine our equations and find A. Here are my free body diagrams. Object dot on the left is the object on the table. I've got normal balancing with my weight because it's not going to accelerate through the table. It's going to move it's just going to either not move or it's going to accelerate to the right. So I have tension pulling it to the right because I have a tension cord, and I have F sub S for static frictional force in the opposite direction, always the opposite direction of the object's motion, or opposite direction of where it is about to be moving, if it's static. FG2, I've drawn proportionately shorter vectors for my weight of 2 kilogram mass because it has a lower gravitational force acting on it. So that's the shorter vector arrow, and I have tension that should be equal in magnitude, but a different direction, upwards on object 2, and that's the same tension as the string for object 1, which is to the right. Alright, so I'm calling to the right positive and down for the second object positive if I expect it to accelerate in that direction. So for object 1, I'm writing out the equation that matches my free body diagram. Object 1 I call my 5 kilogram mass on the table. Sigma F in the x direction for object 1 equals mass of object 1 times acceleration of object 1. I have T in the positive direction minus the static frictional force equals m1a1. I have T minus mu s times the normal force. We said our force, in pink, the equations I wrote, the inequality and equation I wrote under the table there is what we see in the AP equation sheet, which translates to my maximum static frictional force is equal to the mu s coefficient of static friction times normal force. So I have T minus mu s Fn equals m1a1. And that force normal I already found from my free body diagram on my first object of 5 kilograms. That force normal is just m1g, or 5 kilograms times the acceleration due to gravity. So I have that in there as T now, T minus mu s times mass 1 times g equals mass 1 times a1. Now I'm going to go look at object 2 hanging freely there. Just been released as it accelerates downward. It has a force, I say sigma F2 in the y direction equals m2a2. That should be a2 in the y direction. That's equal to m2g, its weight, minus the tension force, because I'm saying down is the positive direction where acceleration would be occurring. So if I draw in there right now, this is the direction I'm calling positive. It's to the right and down, because if down is positive for object 2, that means that the 5 kilogram object is going to accelerate to the right. So I think about my acceleration as a whole direction, even though it's kind of curved around that pulley. Whole one direction. So now I'm doing the same technique here to add both equations together to get rid of my tension force. And there you can see I got my m2g minus mu s m1g equals m1a1 plus m2a2. They must have the same acceleration because the chord's not stretching or changing. If one block is accelerating, the other one has the same acceleration. So I'm factoring out my values again. We'll see it looks very similar to what I had before. A little bit of change. I've divided both sides by m1, m2. And so I still have gravitational acceleration g times some fraction, but this time the fraction includes something about friction equals a. And so I have some m2 minus mu s m1 over m1 plus m2. And here I'm going to substitute those values in finally. But before we say that final answer, look back at what we have written out in my, let's go back just to this equation right here. On the right side, I have my masses and my acceleration, which I factor the acceleration out because we said it has to be the same, and we have the sum of the masses over there. So that's all the mass of the system and the acceleration of the system. That equals what's on the left side, the net force, in both down there and down there. These are representing the net force. So I have m2g, that's the mass of the 2 kilogram object times the acceleration due to gravity. So its weight, that's all the force in the positive direction of acceleration. That's the force that's going to cause this acceleration to happen if it's going to happen. So that's the weight of object 2 just hanging over the table, minus this part. Mu s, the coefficient of static friction, times the weight of the first object, which is equal to its normal force. So this part right here is that static frictional force, And this force right here is the weight of object 2 on the left. So it's like I just have this weight of object 2 minus the frictional force. That's whatever that value ends up being, positive or negative, positive or 0, is going to determine whether this thing accelerates or not. And it turns out that this is going to be just like before. The value of that acceleration is going to be some fraction of g. If I just pick up the 5 kilogram block, or like cut the tension, then if I cut the string, the 2 kilogram block will fall with the acceleration equal to g. If it's connected to the 5 kilogram block and there's no friction, then it's just like what we saw before. I get rid of my mu s, and we're good to go. With friction there, I have some frictional coefficient, and since the table's flat, it's just the frictional coefficient times m1g. If I had an incline, I'd have to find out what that normal force was actually equal to. Anyway, down here back on the bottom right again, we're finally back to this. We've got the value substitute in, and I have 2 kilograms minus 0.4 times 5 kilograms is 2. So I have 0 over 7 kilograms times g is my acceleration, so I have 0 acceleration. So I put this on there, and they balance. Now you can see just from this that if I change, a good follow-up question might be then, okay, what two things could you change in order to cause an acceleration in the positive direction to make 2 kilogram object move downward and 5 kilogram object to the right? I can see from this final equation I have over here, I could either increase this mass, m2, I could increase the mass of the 2 kilogram block hanging over the edge and keep the coefficient of static friction in the 5 kilogram block on the side the same, increase that mass, and I'll have some non-zero value in the numerator. This value down here would also go up, because that's also m2. But that's okay. I'd increase the inertia of the total mass of the system, but I'd also increase the mass that's causing the acceleration, the one hanging over the end of the table, that its weight would go up. So increasing that mass is one way to cause the acceleration. The other way I could cause it to accelerate is to, instead of increasing this number, I could decrease this value here. And if I could decrease that value, then I could cause an acceleration without changing the 2 kilogram mass. So if I had a lower coefficient of friction, so if this was 0.2 instead of 0.4, then I'd have 2 kilograms minus 1 kilogram, and I'd have 1 over 7, and I'd have an acceleration of positive 1/7 g, or g over 7. So that's good to be able to look at that equation and see which things could change in order to cause an acceleration. Alright, this video is super long. So this is a modified Atwood machine. There's one last thing that you can see that we probably won't see anything as complex as this, but you can take this and you should be, after enough practice with this kind of setups with the free body diagrams, you'll be safe as long as you keep track of the direction of possible accelerations. When this kind of question is just now saying, okay, deal with angles now. Okay, so same 2 kilogram and 5 kilogram masses. I got a frictionless massless pulley. There's no friction on the block, on the triangle, on my incline. So here I'm just drawing free body diagrams, assuming a direction of acceleration that's going to be to the right to start. I don't know which way it's going to accelerate, but I got to pick a direction. I said to the right in the down the ramp in the 5 kilogram object's direction that I've decided to call the positive direction. So you can see my arrow that I drew over the pulley is up and to the right, and then down the right side of the ramp is the positive direction. And I've made that match in both of my free body diagrams. You can notice where those directions are defined on the free body diagrams. And notice that I have given angles to my inclined plane, which is actually inclined at different angles on either side of the pulley. So I have to be careful how I draw my diagram. In both those cases, with different angles for those diagrams, I still have normal force perpendicular to the surface, Fg, the weight of each object, straight down, and a tension force that goes upwards along parallel to the incline for each incline. And this one, it's important, I am able to draw resolve my gravitational force vector into the x and y components, the x components in red, the y components in light blue. and that helps me see how the normal force balances with Fg cosine theta, the value adjacent to the angle. That angle is there in between the force that's balancing out the normal force and the gravitational force. That's where that similar triangle angle theta and phi respectively appear. I've called that leftmost angle 45 degrees theta and the rightmost angle 30 degrees phi. On the right side now I've taken to finding out what the balancing of the forces in the y direction for each object are. For each one, their normal force is equal to their weight times the cosine of the angle of the incline. And so I've just done that for this entire right side in blue down here. There's for the first object, sum of the forces in the y direction equals m1 times a1, its acceleration. So that's just looking at its normal force in the positive y direction minus its weight times the cosine of the angle of its incline. Those together have to be 0. It's not going to accelerate through the incline. It's just going either up or down the ramp, which is the x direction. So I found its value of its normal force is something I can calculate. That's something, the value of that normal force is something I need to know if there is friction. There's the second object, the force in the y direction for object 2, and its normal force down there. It has a greater mass, so it has a greater gravitational force acting on it. It has a greater gravitational force component. It has a different angle though, so I have to use that other angle 30 degrees instead of 45, and so it has a normal force value that I can solve for. On the left, up here I have in general the expression that we have for our second law, F equals ma, the sum of the forces equals mass times acceleration, and here's my first object. I'm calling up and to the right on that incline positive direction, so I have the tension force on the first object minus the component of its gravitational force that is parallel to the incline, down the incline. Look at the free body diagram. There's the tension in the positive direction up. There's the component of gravitational force down the incline, parallel to the incline. So that's the force in the positive direction minus force in the negative direction equals m1a1, the mass of the first object, 2 kilograms times its acceleration. Then there's object 2 right here, where it has, in the positive direction, for it is down its incline, so that my acceleration is in the same direction. My pulley is right here. Right, so my acceleration is in the positive direction, so Fg sine phi, which is m2g sine phi right here, is its weight times the sine of the angle. Its angle is phi, which is different from the 45 degree one. That's why it's phi instead of theta. Minus t. T is in the upward, back in the negative direction for block 2, equals m2 times the acceleration of 2 in its x direction. So there should be a1x up there too. So we have those two equations again, similar thing where we have a positive and negative tension. They can go away. When we cancel them out, we'll see what they look like. m2g sine phi is what I have in the positive minus m1g sine theta equals the sum of the masses times the acceleration. So they were just saying the gravitational force component parallel to the incline from the 5 kilogram block minus that component of gravitational force for the other block divided by the sum of their masses is going to give us their acceleration as some fraction of g. Now I've assumed that the positive, I just gave the positive direction in the direction where the 5 kilogram mass was hanging. I assumed maybe that's going to be the direction the acceleration is in. If it weren't, maybe the angles change and it's the 2 kilogram block is able to accelerate the system in its direction to the left, then I would end up with a negative acceleration value, and that'd tell me it's going the other way. I just have to keep track of my directions so that I can see where the resulting direct acceleration is actually pointing. So in my case, I've found that A, the resulting acceleration, is again a very similar looking equation from before. I just have my angle values. Those sine, phi, and sine theta are telling me it's not the full amount of mass that's to be considered because the blocks are sitting at different angles of inclination, and because they have different amount of their weight are actually pulling them in the direction down their respective inclines. So that's why those angle values are in there. Otherwise, the equation looks very similar. It's just some fraction of g. I go on to substitute. Once I have that solved for a, that's where we got to be comfortable with our solving literal equations for the variable we want to know the value of. I have a isolated. Then I substitute in my numbers. Sine 30 I know is 1/2. Sine 45 I know is square root 2 over 2. I just solved that, popped the final bit in the calculator at the end of the day, and I got an acceleration just over 1.5. Alright, so it's positive, so that tells me it's going to be in this direction down the incline. This direction down the incline. Okay, so there's some common dynamics problems. Have fun solving those. Look back at the physics lab. That website that I've linked to before has good practice problems for dynamics. You can go to resource lessons or worksheets on the left side navigation bar and then click on dynamics and then look at some of the different ones. They have things on inclines is one of the headings. Fnet equals MA practice problems. And as well as the Dan Fullerton's practice APPhys problems we have that I posted on Google Classroom. He has a couple in there that involve springs. We do not and did not deal with springs and won't deal with springs until we get to simple harmonic oscillations at the end of the semester. That's it for this one.